Next, let's use Gauss's law to find the electric field due to a spherical insulator that has charge Q uniformly distributed over its volume with radius A. So we did this problem for a spherical conductor. Now we're doing an insulator. We'll see that the insulator is different from the conductor. So let's go to our first line of thought is what is the nature of an insulator and how is it different from a conductor? Well, the big difference is that the charges are not free to move. So in a conductor, all of our charge spreads around, so it goes to the surface or surfaces. That doesn't happen in an insulator. Wherever the charges are is wherever they will stay. And our problem tells us that the charge is uniformly distributed. We can represent that by just drawing a bunch of plus signs all over our sphere. I'll try and draw them more or less evenly spaced out. It's hard to be perfect, but I'll give it a shot. Okay, so that's the first step. Now we know what we think about our insulator, that the charges are here and they will always stay here. They're not going to move around. Next, we write Gauss's law that says the net electric flux through any closed surface is the integral of the electric field over that surface. And that's equal to the net charge enclosed by the surface divided by our constant epsilon naught. So the things we're going to have to figure out is what is the integral E dot dA and how much charge is inside that surface that we pick. We want to pick our Gaussian surface. We want it to match the symmetry. So our object is a sphere of charge. So let's make our Gaussian surface a sphere. We want it to be useful. So let's start by finding the electric field inside the insulator. So let's make the radius of our sphere less than the radius of the insulator. So we're going to pick the radius of our sphere less than the radius of the insulator. Okay, let's draw our Gaussian surface. Why don't I pick a bright red so it's easy to see? So there's our Gaussian surface. It's a sphere. It's concentric with our insulator. And what else? It's a sphere, it's concentric, and the radius is less than the radius of the insulator. So now what we'd like to sort out are the two parts of our expression. What is the integral of E dot dA and what is the charge enclosed? Let's start with the charge enclosed. So this is not that simple a concept, and we've tackled this idea once already when we did our line of charge. So we're going to use that concept again, and let's start by asking, is the total charge enclosed or only part of the charge? And if you want a visual representation, you can go ahead and count up the plus signs. Do we have all of the pluses inside this Gaussian surface, this red dotted line, or do we only have some of the pluses? Well, I would have to say that we only have some of them. Q enclosed is a fraction of our total charge Q. That's because some of the pluses are outside the Gaussian surface. That means they don't contribute to the electric field. And some of the pluses are inside. They do contribute. So now the big question is, how are we going to find that Q enclosed? In a previous lecture, we defined charge density, and for 1 dimension, it's charge divided by length. 2 dimensions, charge divided by area. 3 dimensions, it was charge divided by volume. We have a 3-dimensional spherical insulator, so we're going to use our volume charge density. Okay, so now our Q enclosed, we're trying to find out how much charge is inside the Gaussian surface with this radius. Well, the net amount of charge inside there is going to be equal to the density times the volume. So the density has the symbol rho, and the volume of our Gaussian surface is the volume of a sphere with radius little r, 4/3 pi r cubed. Okay, now we haven't technically defined our rho yet, so let's define our rho. Previously, we said it was charge divided by volume, and that's true. It's the total charge divided by total volume. Our total charge is the net charge Q, and our total volume is the volume of the whole spherical insulator, 4/3 times pi times its radius, A, cubed. Okay, let's put this expression in our Q enclosed. So I've got Q over 4/3 pi A cubed times 4/3 pi R cubed. Let's see, we have some cancellation. The 4/3 cancels and the pi cancels. So we're left with Q times R cubed over A cubed. Let's write down that result. So Q enclosed equals net charge Q times R cubed, the radius of the Gaussian surface, divided by A cubed, the radius of the sphere. So we see that our charge enclosed, the amount of charge inside this Gaussian surface, is indeed a fraction of the net charge. The amount of charge enclosed depends on how big this Gaussian surface is, and that makes sense. Next part to tackle now is the integral of the electric field over the area. In our insulator, we have a radial distribution of charge. Everything is spherical. That means that the electric field has to be radial. So when we have spherical charges, we have radial electric fields. Our electric field vector will come straight out something like this. So we're trying to figure out what is the integral of E dot dA. The integral of E dot dA is E times dA times the cosine of the angle between the electric field vector and the area vector. We've already drawn our electric field vector. Now we have to pick our dA. That's a little bit on our Gaussian surface, so we can shade that in. Maybe I'll just use a different color. There's a little bit on our Gaussian surface, which is a sphere. The direction is straight out of the sphere. So our area vector is radial outwards, our electric field is radial outwards. Those two vectors are parallel. So I've got E times dA times the cosine of 0. Cosine of 0 is 1, so I'm left with E times dA. The electric field, if we're a constant distance from the center and all of this charge is uniformly distributed, then the electric field has to be constant at that same constant distance. That means E comes outside the integral. So I've got E times the integral of dA. The integral of dA is A. That's the area of the Gaussian surface. The area of the Gaussian surface. Here's where you have to be careful that you don't get confused between area and volume. When you're working quickly, sometimes it's easy to get those just a bit tangled. The area of a sphere is 4 pi r squared. Okay, now we know what the integral of E dot dA is. We've already sorted out Q enclosed. Let's put it all together. So net electric flux equals the integral of E dot dA equals Q enclosed over epsilon naught, E times 4 pi r squared equals Q times R cubed over A cubed. Also got epsilon naught in the denominator. Let's see, I've got, the only thing can cancel is I can divide both sides by r squared. That leaves me with an r on the right hand side. Solve for E and I get E is 1 over 4 pi epsilon naught times Q times R over A cubed, and the direction is going to be radially outward. Okay, this is an interesting result. This is different than the conductor. In the conductor, the electric field inside was equal to 0 because all of the charge went to the surface. On the inside, not all of the charge is on the surface, some of it is on the inside, so there is an electric field inside an insulator. And that electric field is proportional to the distance from the center, so it's going to be linear with R. Next, we'll do outside the insulator. So now let's find the electric field outside of our insulator. We'll begin by writing Gauss's law. We'll go through the steps more quickly now because we've done them quite a few times. E dot dA equals Q enclosed over epsilon naught. We want to choose our Gaussian surface. We want it to be symmetric and useful, so let's pick a sphere with radius greater than the radius of our insulator. So our Gaussian surface is a sphere with R greater than A. The two things we need to sort out, what are Q enclosed? What is the integral of E dot dA? Q enclosed equals how much charge, how many of the plus signs are inside this dotted line we drew? Well, that would be all of the charge equals Q because all charge inside. If you're thinking this sounds familiar, then that's a good thing. We're following the steps now that look a lot like what we did for the conductor. Okay, the integral of E dot dA can go through and show all of the steps. We'd have to pick a little bit of this surface that has a little bit of area, dA, that's radially outwards. The electric field is radially outwards and is constant at a constant distance from the center of the sphere. And we get E times 4 pi r squared. I won't go through all those steps again because it's probably a bit tedious to watch. Okay, now we'll put it together. The integral of the electric field dotted with the area is Q enclosed over epsilon naught E times 4 pi r squared equals Q, our net charge, over epsilon naught. So our electric field is 1 over 4 pi epsilon naught times Q over r squared. It's a positive charge with spherical symmetry, so the direction is outwards. I'll just write out because I don't have quite enough room for outwards. So what we notice here about our spherical insulator is that the electric field outside is just like a point charge and just like a conductor. So once we're outside of a spherical charge, the point charge, the conductor, and the insulators all look exactly the same. They have the same behavior. And just last little bit to point out, if you wish to represent that with K, Coulomb's constant, you certainly may. Now, of course, because we're physicists, we graph everything. So let's do a plot of the electric field as a function of distance from the center. So inside the sphere, we know that it's linearly proportional to the radius r. So we'll put our electric field on the vertical, we'll put our distance from center on the horizontal. An interesting spot to watch out for is what happens when we hit the surface. So let's just indicate that spot. So if r is less than a, we're inside. And what happens inside is that we have a linear behavior. So the electric field starts at 0 when r is 0, and it increases to some value. That value is kind of interesting, so let's see what we can say about this value. At r equals a, the electric field is 1 over 4 pi epsilon naught times q times r, which is a, divided by a cubed, which is 1 over 4 pi epsilon naught q over a squared. What's a little bit interesting about this result is if we put r equals a in our expression for outside, we'll put in r equals a here, we get exactly the same expression. That's a good thing. We get the same answer whether we're coming at it from the inside or the outside. So let's label that on our picture. Maybe made it a little bit too high. K q over a squared, where k is 1 over 4 pi epsilon naught. Okay, what about once we're outside? Once we're outside, our electric field falls off as 1 over r squared, just like it does for a conductor or a point charge. So something like this. So when we're outside, at r approaching infinity, the electric field is approaching 0. The curve as we get to a big value of r is that the electric field goes as 1 over r squared. And at r equals a, we have kq over a squared. So let's just label this for the outside. So this is a pretty common thing to do, to find the electric field in the vicinity of an object and then graph that electric field. Let's do an example now with some numbers. We have a thin-walled hollow sphere. So it looks something like this. Maybe imagine like a bowling ball. So it's got a wall, but it's empty inside, or a balloon. The latex of the balloon would be the wall. It's got a radius of 0.250 meters. And it has an unknown charge distributed uniformly over its outer surface. So there is charge, and it's all on the outside. At a distance of 0.3 meters from the center of the sphere, so at a distance of 0.3 meters, sometimes it's good to draw as we go. Please try and imagine here that I've drawn lovely spheres instead of these kind of distorted egg shapes. 300 centimeters or 30 centimeters. From the center of the sphere, the electric field points radially inwards. Let's pause and draw that electric field. And we know the magnitude is 1.8 times 10 to the 2 newtons per coulomb. So the electric field looks like this. So let's think about what else we can take away from what we just figured out and what we just drew. If the electric field points inwards, this tells us that the charge on the outer surface of the sphere must be negative, because electric field points towards a negative charge. So Q is less than 0. The question is asking us to find the charge on the sphere. So let's use Gauss's law to accomplish that. We'll start by writing down Gauss's law. The net electric flux for a Gaussian surface is the integral of E dot dA equals Q enclosed over epsilon naught. Now we pretty much have our Gaussian surface built in for us, because we know the electric field at 0.3 meters away from the center, and we drew a sphere. So this dotted line that we drew, that's going to be our Gaussian surface. It's a sphere with radius equal to 0.3 meters. Okay, and we're trying to find what is Q enclosed. So let's start with the left-hand side of the equation. What is the integral of E dot dA? So the integral of E dot dA is equal to the integral of the magnitude of the electric field E times the magnitude of the size of an area element times the cosine of the angle between those two things. So an area element is a little bit of the area on our Gaussian surface. The direction of that vector is straight out from the surface. So we notice here that our electric field is radially inwards, but our dA is radially outwards. Those two vectors are anti-parallel, so the angle between them is 180 degrees. Cos of 180 is -1, so we've got minus the integral of E times dA. Electric field is constant everywhere on the surface of that Gaussian surface, so my E comes outside. The integral of dA is just the area of the Gaussian surface, which is 4 pi r squared. Okay, now minus E times 4 pi r squared can go in for the integral of E dot dA. Then we'll be able to solve for Q enclosed. Minus E times 4 pi r squared equals Q enclosed divided by epsilon naught. So our Q enclosed, that's the net charge inside our Gaussian surface. Q enclosed equals minus E times 4 pi r squared epsilon naught. Don't have tons of room, so I'm going to fill in for E. It's 1.80 times 10 to the 2 newtons per coulomb. R is the radius of the Gaussian sphere, 0.3 meters. Epsilon naught is the permittivity of free space, 8.85 times 10 to the minus 12 with units of coulombs squared over newtons times meters squared. When I do that, what I get for my answer for Q enclosed, I get minus 1.80 times 10 to the minus 9 coulombs.
So Q enclosed is whatever charge is inside of our surface, and we know that it's negative charge and it all resides on the surface of the sphere, so we could draw little negatives if we wish. And the net charge enclosed is the charge on the surface of the sphere. So the charge on the sphere is minus 1.8 nanocoulomb.